Hello, and welcome back to Learning with Lee. In today's episode, we are going to continue our discussion of linked lists, structs, and their use in the merge sort algorithm. In particular, we are going to continue to look at the different functions that we've created in order to make it a bit easier to use these two structs and to use linked lists in general than having to manually code out these functions everywhere we would actually need them. In the previous episode, we took a look at how to create a list and how to insert elements into that list, as well as the corresponding methods in link that allow us to create links and insert links. So, what we're going to do now is we're going to examine how we clean that all up when we are done. And that's done using this delete list method right here, delete list function. And what delete list does is it first goes through your list and deletes each element in the list. And the reason why we do that is that if we take a look at our earlier example here of this, where we have some pointer in to A, and this is our first element in the list. If I end up deleting whatever this object over here is, which happens to be our linked list, and I just delete that, all of this still exists in memory because of the fact that we're using the heap. So the first thing we have to do is we have to go through and basically delete A, delete B, and we have to avoid having any situations where, for example, things still have a reference to A when they shouldn't after we've deleted it. Things might still have a reference to B, and so on and so forth, as well as we have to fix things up so as we don't end up with any null pointers that could give us errors. So, for that, what we're doing is basically we're using this pop function, which I'll get into in a second, in order to get the first element off of our list, which then also fixes the rest of the list, so as that basically we find the first element, we can delete the first element, and then we can get the next element in the list and just continue until there's no items left in the list, which happens to be represented by pop returning a null pointer. Then once we're done with freeing each element in the list, we can then free the list itself. Because once all of these things here have been eliminated from memory, we're safe to remove this because it's not pointing to anything that would end up leaving a memory leak behind or taking up extra space there and possibly causing incorrect behavior. So what pop does, and the reason it's named pop, is that it comes from two different methods, push and pop, which happen to be commonly used for things such as stacks and queues. And you can think of a queue similar to how you would think of a line at somewhere like Disney World, in which you enter at the back of the line, and eventually you get off into the ride at the front of the line. And a stack is just the reverse. It would be whoever ends up entering the line at the end gets to come off first. And the common thing is that you push something either onto your queue or onto your stack, and then you pop something off, which is basically, in the case of this, whatever the first item is. So we grab the first item, store it in a link pointer, we remove its links so as that it's adjacent, in case you remember what this does over in here. We end up removing these links to it and updating the links around it, and basically with it then pointing to itself. What we then do is that we reduce the count by 1 and we return that item. Technically there is one other thing that we have to actually do. Oh wait, no, we don't. Because in here, one of the things you'll notice is that this also, because of how remove links works, remove links ends up returning the item after whatever we end up dealing with. So if I head down to remove links, what we're looking at here is that it'll fix that one, reset it, and then it returns the next item in the list. And what we then do is we update our first item in the list to point to the next item, so that the only pointer we have to this first item that we referenced up here is this link itself, which is what we then return. Basically what we're doing then is grabbing this item, cleaning up all the pointers, reducing the size of our list by 1, and returning the item that just got removed from the list. And that allows us to free it up here without having it pointing to any of the other objects, without having any of the other links in there pointing to it. So that's why we end up using pop, and we'll use pop a fair amount throughout this. The next thing we have is we have this split method. And to get into what the split method does, let's hop on over to how we're actually sorting this. And this is going to look very similar to our other merge sort things, however it's a bit cleaner to a certain extent. because of the fact that we actually don't have to deal with any of the dynamic memory allocation up in this method that we had to in such as merge sort alternative, in case you want to open that one up and take a look at it. But what this one does now is it just passes on to merge sort recursive. And what merge sort recursive is going to do is it's going to first check whether or not our count is only a single element, and that's going to split the list to two sublists. And the important thing to understand is that we're just reusing this list pointer here for one of those two lists, and we're getting the second list in split list here. So if we head over to see how that's actually implemented then over in here, what we do is we create a new list that will be our second list in here. So you can sort of envision it such as if I have this one up here, what I'm going to do is I'm basically going to split this list along here, make this guy point over here, make C point over to A, have A point back to C, and have this guy point back to here. And that happens to be the way in which we're going to split it, and then we can split it again over here so that then it's B and C in one list, A all by itself in another list, then split B and C. And that allows us to fairly easily, fairly rapidly go through and to split these lists up. And one of the things that we're going to take a look at in the next episode is the difference between how we're doing this now, which is using the heap using this new list method, and if I were to change it up so as that then, in case I end up looking over here, if I end up using this so as that this ends up being using the stack rather than the heap, then we'll see how that actually impacts our performance, just to take another look at the differences between dynamic memory allocation versus using the stack. Then, once we have our new list, and in here we just are checking that we have at least 2 items in the original list. Because in case there's only 1 item in the original list, there's no reason to move it over into the second list. And if it has no items, we're obviously not going to be moving any items back and forth. And as such, this new list here is going to return a list that has a null pointer for its first item, in case you remember how we have this set up down in here, in which we have this null pointer and setting its count to 0. We're going to end up with that, so basically an empty list. Then, down in here, what we're going to do is we have to find basically what I like to call the split link and the last link. And the last link is very easy to find. In this case here, our last link would be this guy right up here, because it's the one before our first element. And if you remember how I drew our little line here to say how we're cutting it off, what we're going to do then is we need to figure out which one I need to move so as that I can make these pointer changes so as that it's effectively 2 linked lists. And that's going to be our split element. And I'll just call that S for now. And what we end up doing then is, the way in which we find that is via this little bit of math right here, as well as then we have to jump through the pointers to actually find that element, which is what this is doing. And the important thing to note about this right here is that if you have, say, 3 items, you're going to wind up with 2 items in your split list and only 1 item in your source list. If it's even, it'll wind up, say in case you have 4 items, it'll wind up 2 and 2. However, it's a bit cleaner this way, and it doesn't really matter one way or the other how you end up doing it, because no matter how you end up doing it, the same number of pointers need to get changed in either case. So then what we end up doing is we have to disconnect. Basically, well, what this is doing is this happens to be dealing with the item that's prior to the split link. So in this case here, this would be C. Because right now, without iterating through it a second time, the only access we really have to C is through having found our split link. And we found that over in this loop up here, where we go up until we reach this half count, and we just move through one further along through the linked list. So basically we go here, here, and then we end up here. And technically I did a bit of a shortcut in that we actually start at B, because we know for a fact that A is never going to really be our split item. If we wind up anywhere, we're going to split starting at B. So what we end up doing then is we can end up going, okay, we find S, we need to update C to point to A, which is what these first 2 lines are doing. Then what we have to do, and one of the important things about this is that this is also updating A to point to C, so that when we end up changing our last element to point over here, we don't once again need to re-update A to no longer point to that one, because at this point it no longer does. Which is also one of the reasons why I'm caching it in this last link pointer up here. And that's because otherwise I would have to iterate through the entire list until I got to it. So it's a bit of an efficiency saver and time saver, so we update those, then down here we just update it so as that our split link points over here, and this guy points over here. And that's really all that we have to do, with the exception of one other thing, and that is that we need our split list, in case we look over here, and right here, we're making its first item equal to the split link. So basically we're creating our new list, and we're having it point over here. So I'll just call that one NLL for new linked list. And that one's pointing over there, and at that point we've effectively split out these two lists. Once we're done with that, it's basically the exact same on this. We keep splitting up the list at each level of our merge sort. Then we merge them back together. And the merge is slightly different than it was before. The first thing we're doing is that we're creating some link pointers, and I have them initially assigned to null pointer, and that's so as that in case either of these lists is a null pointer, I don't have to worry about getting any errors for trying to access an item of a null pointer. Because in case I had something such as effectively that's going to give you an error even if you have it in a variable here. Because if I were to comment out that section there, this would end up giving me errors when I end up running my program, and it would cause the program to crash. So you need to make certain that you can actually use the items that aren't null. Then, down in here in the while loop, we effectively have this here, which once again is to a certain extent a comparison of checking this, but it's also checking not only are these not null for our lists, but also that the first item in each of those lists is not null. So, and the reason for that is that we're going to have to do a comparison between those two items. And in case we're trying to compare some value within those, we need to know that they aren't null pointers. So then what we're going to do is we are going to head on down here, and we are going to end up using this logic to determine our merge. And what this does is it ends up allowing us to go first, and the way in which this will happen is that in case I treat this as though we have some items over here in one list, some items over here in another list, and we'll just call this A, B, and C, and this one here D, E, and F. What we're looking at then is that in case, what I'm going to do, and right now these are just linked up around like that, and same thing for down here, and I have a pointer into each of these, which is important to remember. What I'm going to do is I'm basically going to start at each of these first elements, because these lists here are already sorted by the nature of merge sort. So I don't need to worry about resorting them at this point. And I just compare A to D. And in case A is less than D is, I just move on over to B for what I'm checking, and I compare B to D. And I can keep moving over, and in case I've gone through every element in this list, I just can append whatever's down in this bottom list and whatever's left onto the end back here. And that's a pretty easy thing to do. Alternatively, if D happens to, let's say, be less than A, I basically have to move D up into here. So I have to remove it from this list, and as you'll see, we'll use the pop function to do that. Then I have to move this item up into here and insert it. And in case it's at the first element, I need to update it so as it is the new first element. So in case D is less than A, it doesn't wind up accidentally at the back of my list, but rather at the front of the list. So what we end up having to do in here is that if this happens to be less than A, we need to use our insert here. And this ends up using this, does this insert. There is one possible problem with this, and that's that right now it's ambiguous between whether it's at the back of the list or at the front of the list. So the way to solve that is basically just to have a check here And this happens to be that in case and we can just do this way, so if our link in the A list is equal to the first element in the A list, then what we need to do is we need to end up updating A list. So A list and its first item needs to be equal to, in this case here, a first, and scooch this over to previous item. And that will take care of making certain that we remain sorted in this merge. Then, what we have to do beyond that is, because of the fact that we ended up doing that, we need to move our B list, or B link, since it's our present link in the B list, to the next item down the list. And because we used pop, it's going to be in that first item slot in there. Alternatively, in case we've already completed it, and because of the fact that we are doing this merge in a while loop, we just are going to insert the rest of these one at a time onto the back of the A list. It could be a bit more efficient in case we were to create a variant on insert that ended up allowing us to take in multiple link pointers, or to take in, say, a list pointer, and basically let you know where you need to have it inserted into that list, because of the fact that then we only have to change 4 pointers. However, for now, this is good enough. Then, the other alternative is that down here, in case we end up having the A link before the B link, like I had said initially, we need to move from A over to B so that we can then compare that one with D to see if D should go before it or after it. And that's the general way in which we're going to be doing this merge, and it works out fairly easily and fairly predictably. So, that's really the majority of what we hadn't covered in the previous episode. The only thing we haven't looked at yet is, if we head on over into here, we have not yet looked at this print function, and we haven't looked at our generate random list function. And because we never actually looked at the ones for arrays yet, I'll probably actually split those off into their own episode later on, in which we go over both how I did that for the arrays as well as how I do it for the lists. And we can cover some of the libraries involved, some of the nuances of random numbers and nuances of output. And that'll be a decent enough topic on its own. So, thank you very much for watching. Spend some time going through this and seeing what you can figure out about how it actually works. And have a wonderful day.